Welcome to this guided practice. We will solve a collection of square root and perfect square problems, step by step, with clear visuals. First, we will find square roots of fractions, then judge some true or false statements. Then compute square roots by prime factorization, check whether numbers are perfect squares, and finally adjust numbers to make perfect squares. Problem 7. Find the square root of each fraction or mixed number. We use the idea that the square root of a fraction equals the square root of the numerator divided by the square root of the denominator. Part 1. The square root of 144 over 221. We split the root across numerator and denominator. The square root of 144 is 12. 221 is not a perfect square, so we leave its root as is. Optionally, we can rationalize the denominator. Part 2. 7 and 18 over 49. Convert the mixed number to an improper fraction. 7 times 49 plus 18 equals 361 over 49. Now take the square roots to get 19 over 7, which is 2 and 5/7. Part 3. 6 and 1/4. Convert to 25 over 4. Then take the root to get 5 over 2, which equals 2 and 1/2. Part 4. 4 and 25 over 36. That is 169 over 36. Taking roots gives 13 over 6, which is 2 and 1/6. Problem 8. Decide true or false. We will show each statement and simplify it on screen. Statement 1. The square root of 32 divided by the square root of 8 equals 2. Yes, because it equals the square root of 4, which is 2. True. Statement 2. The square root of 625 over 1024 equals 25 over 32. Both numerator and denominator are perfect squares. True. Statement 3. The square root of 28 times the square root of 7 equals 2 root 7. The left side is the square root of 196, which is 14. 2 root 7 is about 5.29. Not equal. False. Statement 4. The square root of 225 plus the square root of 64 equals the square root of 289. 15 plus 8 equals 23, while the right side is 17. False. Statement 5. The square root of 1 and 400 over 441 equals 1 and 20 over 21. Inside the root, we have 841 over 441, whose root is 29 over 21, not 41 over 21. False. Problem 9. Find each square root by the prime factorization method. We form pairs of identical primes and take one from each pair. Part 1. 1156 equals 2 times 2 times 17 times 17. 1 from each pair gives 2 times 17 equals 34. Part 2. 4761 equals 3 times 23 times 23. So the root is 3 times 23 equals 69. Part 3. 9025 equals 5 times 5 times 19 times 19. The square root is 5 times 19 equals 95. Problem 10. Check if each is a perfect square. A whole number is a perfect square only when every prime factor appears an even number of times. 725 equals 5 times 5 times 29. 29 is unpaired, so this is not a perfect square. 190 equals 2 times 5 times 19. No pairs, not a perfect square. 841 equals 29 squared. So yes, it is a perfect square, and its square root is 29. 1089 equals 33 squared. So it is a perfect square with square root 33. Problem 11. Find the least number to multiply 1800 so that it becomes a perfect square, and then give the square root of the new number. Prime factorize. 1800 equals 2 cubed times 3 squared times 5 squared. Only one factor of 2 is unpaired, so multiply by 2. The new number is 3600, and its square root is 60. Problem 12. Find the smallest number to divide 10,985, so the quotient is a perfect square. Factor. The number equals 5 times 13 cubed. To leave only pairs, divide by 5 times 13, which is 65. The quotient is 169, a perfect square. Problem 13. Is 2,352 a perfect square? Prime factorization gives 2 to the fourth times 3 times 7 squared. The factor 3 is unpaired, so it is not a perfect square. Multiply by 3 to complete the pair. The new number is 7,056, and its square root is 84. Problem 14. Find the least square number divisible by 8, 12, and 15. Start with the least common multiple, which is 120 equals 2 cubed times 3 times 5. To be a perfect square, exponents must be even. Multiply by 2 times 3 times 5 to make the exponents even. The result is 3,600, which is 60 squared. Great work! We practiced square roots of fractions, judged true or false statements, used prime factorization for square roots, tested perfect squares, and adjusted numbers to build perfect squares. Keep these patterns in mind. Split square roots across products and fractions, and make prime exponents even to form perfect squares.